Okay, good morning, gang. Today we're going to finish up all of the material for exam one. The last little bit of things we have to talk about before exam one are complex numbers. We haven't gotten to talk about complex numbers in any detail yet. I see that many of you, in fact, most of you have finished the, or at least started the complex numbers homework, which is great. It's the last homework on quadratics, and it's the last thing that we have to do before the test. So I'm going to kind of lay out a roadmap here, get all the dates squared away for the exam so everybody knows exactly what's going on. And then we're going to jump in and talk a little bit more about complex numbers, or talk a little bit about complex numbers, a little bit more about quadratic functions. So where are we here? Let's do it like, we'll do it like this, and like this, and like these. Complex numbers are pretty cool. It turns out that there's a whole universe of mathematics connected to complex numbers called complex analysis. You can study functions of a complex variable, meaning you let the input be a complex number and you consider the output as being a complex number. The graphs of such functions are four-dimensional because they have two-dimensional input and two-dimensional output. Don't stress, I won't do that to you here. But just a little bit of neat information. So this is MAC1105, section 007. It's a lecture. And today is the second. So today we finish the material for exam one. Namely, we're going to talk about it's homework 9 on complex numbers and quadratics with no real solutions. And that's it. And we'll talk a little bit about the test. Okay, so let's get the announcement-y test stuff out of the way first. I don't think we'd set a date for exam one yet, right? Looking back over my last few videos, I'm pretty sure we had not yet set that date. So I do want to go ahead and set that date in stone. The rule that I usually follow is on the day that I finish the material for a given exam, I set the date for the exam to be 1 week later. That way you guys have a week to study, do whatever you want to do to prepare for the test. So today is the day we're going to finish the material for exam one, which means the date for exam one will be the 9th. This will be during class. And we will proctor using both honor lock, that'll be on your computer, and Zoom on your phone. The way we're going to do this, your phones are going to be set up on your desks so I can see your workspace, your hands, your paper, and then honor lock will be doing its normal thing, watching your web traffic, recording your face, recording your screen. If you have any concerns about this, don't hesitate to talk to me. I will give you some really detailed instructions, and we can do a practice run in office hours to make sure everything is going to go well. But that's how it's going to work. So you're going to need to install Zoom on your phone, and you're going to need to make sure you have honor lock installed on Chrome. Make sure Chrome is up to date. Sometimes the newer versions of honor lock don't work on old versions of Chrome. I haven't actually run into that, but they keep warning us about it, so it's not a bad idea to be careful. But that's the deal. All right, so the exam is going to be on the 9th. And exam one will cover covers all the material we've been through so far. So I think probably the easiest way to break that down is by homework numbers. It's just homework 1 through homework, 9, right? Yeah, homework 1 through homework 9. So of course that's like functions and the definition of a function, different ways of describing a function, linear functions, lines and slope, average rates of change, increasing and decreasing functions, and then quadratic functions, models that we can use factoring, putting quadratics into vertex form, finding maxima and minima by putting into vertex form, those real world problems like the rocket problem last time where we had to find a max height by finding the vertex, that sort of stuff. And then finally, what we're going to be doing today, which is on complex numbers. One last little thing, I should say quiz 3. Quiz 3 and homework 9 are due next Tuesday. All right, so I really want everybody to get a chance to finish these. And since we hadn't talked about homework 9 and quiz 3, like I said in class last week, I went ahead and extended those. So you don't need to panic if you haven't gotten them done today, or if you'd like to go back and work a little bit more on any of them. They'll be due next Tuesday, which is the day of the test. Okay. Next class, I'll talk about this during next class. I'll assign you guys a little project, a little kind of take-home project. You can treat it as sort of a study guide. It'll address some of these things, but not all of them. Of course, I can't put everything onto a project that you have on the test. It would be huge. That wouldn't be fair. There's also a review here. Review for test 1 that you can do in Pearson in my math lab. So these are the main tools to prepare for the test. First, make sure you study the homework problems. Make sure you can do all the homework problems on your own. If you want to condense that, if you've done all the homework problems, but you don't want to go back through all of them, make sure you can do all of the quiz problems on your own, like print the quizzes. Make sure you can solve those without using any of the little help things. After you've done all the homework and the quizzes and you're confident you can do all those on your own, go through the review and treat the review like a little test, right? You can time yourself and just pretend like you're taking the test. Go in there, bang out the review. If after you finish all of that, if you still want more stuff to practice, come talk to me in office hours or send me an email. I can get you some more materials. There will be an activity this Thursday that we're going to do in class. And there will also be a little project that I'll give you to work on over the weekend. But those are meant to look at more specific things. Those aren't meant to be as broad. So do the homework first. Make sure you can do all those. Do the quizzes. Make sure you can do all those. Do the review in my math lab, and you should be good to go. And then there are the activity in class this Thursday where we'll work together to try to bone up on a few things. And there will be also a little take-home project over the weekend. Any questions about the announcement-y sort of stuff? I should add these here, right? Activity in class this Thursday. That's activity 2. And there will be a project. Project 1 will be sent out Thursday and due on 2/9. I feel like that's enough on the bookkeeping stuff. If there are not any questions on this stuff, then I am going to go ahead and start on the new mathematics content for the day. Last call for questions on when's the test, or what's on the test, or what do I have to do over the next few days, anything like that. All right. So complex numbers. Definition. A complex number is an object of the form A plus B times I, where A and B are real numbers. And I is the square root of -1. So the obvious catch here is that there is no real number that you can square it to get -1, right? When you square a number, the result is always positive. So these things kind of arose by looking for solutions to quadratic equations that at first appeared to have no solutions. For example, the solutions to x squared plus 1 equals 0 are complex numbers. All right, so in the past we've said that this equation and equations like this have no real solutions. The reason I always use the word real there, the reason I always say no real solutions rather than just no solutions, is because there are always solutions to these sort of equations. It's just that sometimes they're non-real complex numbers. So I can solve this one by taking square roots because there is no x term. It's just an x squared and a constant. I subtract 1 from both sides like that. And now I take square roots. On the right-hand side, I get plus and minus square root of -1. So I have here x equals plus and minus the square root of -1. And remember, this is the number I. So these solutions are x equals plus and minus I. There's so much I could say about complex numbers that I get a little bit mentally lost trying to introduce people to these things because they're so beautiful. The geometry of complex numbers is really fascinating. Solutions to polynomial equations, when you look at all of their solutions, including the complex ones, they form these beautiful patterns in the complex plane. All of that is really good stuff. But in order to talk about any of those things, we need to talk about what the complex plane is. So I suppose we should do that next, and then we'll talk a little bit about the arithmetic of complex numbers. Just to be clear what I mean when I say that x equals plus and minus I are the solutions here, the two solutions are x equals I and x equals -I. And you can check that these solve that equation. I'll just check that x equals I solves x squared plus 1 equals 0. How would I do that? Well, I'd plug in I for x, and I would get I squared plus 1 equals 0. What is I squared? Well, if I is the square root of -1, here's another way to define the number I. If I is the square root of -1, that's the same thing as saying that I squared is -1. So this I squared right here, this is -1. So this is just -1 plus 1 equals 0, which is the same as 0 equals 0. So that is indeed a solution. This definition is actually the one I prefer, right? It's thinking of I as the number such that I squared is -1, but it's the same thing as saying the square root of I is the square root of -1. So I kind of think of it like this. Most people kind of think of it like this, and they mean the same thing. This is the form we actually use it in, right? When you go to do arithmetic and algebra with complex numbers, this is the thing that matters. Questions on this? I said, I'm very excited to show you guys the complex plane and all the beautiful geometry here, but we need to get a little bit comfy with computation first. So let me grab a few problems from the associated homework set, make sure we're feeling good about square roots. We all know how to work with square roots. And so I have a few statements here that are going to involve complex numbers, going to involve the number I. So I would like to just see if we can't sort these out. I'm going to kind of show you how I like to work with square roots. The square root of -4, I can think of as the square root of -1 times +4. And while square roots don't play nice with addition or subtraction, they do play nice with multiplication. So I can think of this as the square root of -1 times the square root of 4. Well, the square root of 4 is 2. The square root of -1 is I. So this is I times 2, or most people would write that as 2I. Is everybody comfy with that? So there's a few big ideas here. That's that the negative of any number is just -1 times the positive version of that number. And then the square root symbol, you can split him up over multiplication. If you have a square root of a product, you can take the square root of each of those pieces separately and then just multiply them. Only works like this for multiplication and division. Doesn't work like this for addition or subtraction. Square roots are finicky about addition and subtraction. So if I wanted to do this with the square root of -24, I would write that as the square root of -1 times 24. And then say, okay, well, that's the square root of -1 times the square root of 24. And at this stage, I could say, okay, this piece is I, and this is the square root of 24, and just call it a day. But the square root of 24 can be simplified a little bit. It's not a perfect square, but there is something we can do here. Who can help me simplify the square root of 24? What's the key to doing that? Are there any perfect square factors inside 24? Yeah, Gabe's on the right idea. He says there's a 2 that can come out. Why is there a 2 that can come out of the square root of 24? You're correct. Why is that true? You can respond in chat or hold down your spacebar to talk. Or if anybody else wants to try and explain. So the square root of -1 I'll write as I. The square root of 24, would we all agree that that's square root of 4 times 6? Yeah, very good. Perfect, William. Perfect. 4 times 6 is 24. You hit it right as I started writing it here. So 24 is 4 times 6. And now the same sort of thing I did here where I split up over multiplication, I can do that again. This is I times the square root of 4 times the square root of 6. And the square root of 4 is 2. So this is I times 2 times the square root of 6. And most people would write that as 2 root 6 times I. And I like to put a little tail on the back of my square root so you can tell where the square root symbol stops. I advise you do the same. So I hope everybody understands what's going on here. Playing around the square roots, you'd be surprised how many Calc 2 students I have that don't understand square roots. Don't be that guy, right? Or that girl. You can do this. This is not that bad. If you want to simplify a square root of a number that isn't a perfect square, right? You can't see what the square root is right away. Try to factor that number into perfect square pieces and other shit. I know that 24 is divisible by 4, and I know that 4 is a perfect square. So I can write this as 4 times 6. There are no perfect square factors of 6, but 4 is a perfect square. So I take the square root of those two things separately, and I'm allowed to do that because this is multiplication, and square roots play nice with multiplication. I is I, that's the square root of -1 that we pulled out right away. The square root of 4 is 2, and the square root of 6 is just the square root of 6. There's not anything nice that can be done with the square root of 6. It's an irrational number. We just have to leave it as it is. All right, the square root of 36. The square root of -36. Same sort of logic, right? This is square root of -1 times the square root of 36, which is I times 6, or 6I. Beautiful, thank you, Jacob. All right, what about this last guy? Don't write this down, but I want to ask you a question. Is this the same as -2 plus and minus 4 minus 5 all over 3? Can I do this? Question mark, question mark. Don't write it down. I'm just asking you. Is this allowed? The square root of 16 is 4. The square root of 25 is 5. So are these equal? Yeah, Gabe's correct. These are not equal. Yeah, Mark and Gabe, thank you guys. Can anybody offer an explanation? Why are those not equal? Yeah, it's an order of operations thing, right? You have to think about the inside of the square root as being in parentheses. Really, the square root is a power, and powers take precedence over addition or subtraction in your order of operations. You've got your PEMDAS, right? So this is not kosher. This violates the order of operations. Okay. In other words, when I said up here that square roots play nice with multiplication, but don't play nice with addition or subtraction, this is exactly what I mean. Right? This is what I mean by square roots don't play nice with addition or subtraction. Okay, so we don't want to do that. But what we can do is simplify under the radical, then take the square root. So this is -2 plus and minus the square root of 16 minus 25. What is that? Well, let's see. 25 minus 16 is 9. So this is -9. Yeah, perfect. And now I have a negative under the square root here. So the 9 happens to be a perfect square. So we don't have to worry too much about how to handle the 9, but the negative is going to give me an I. So this is -2 plus and minus I times 3 all over 3. And I can clean this up. This is the same as -2/3 plus and minus I times 3/3. Right, just taking this over this, plus or minus this over this. You can think of the I as being upstairs in the second fraction, or you can think of it as being up front. Normally, we like to write complex numbers in the standard form, which is that A plus BI. So this would be -2/3 plus or minus I times 3/3. Well, 3/3 is 1. So the two numbers here are -2/3 plus I and -2/3 minus I. And two complex numbers like this, where the real part here is the same, but the imaginary part, the part with the i's, have different signs. These are called complex conjugates. Right? In general, A plus IB and A minus IB are called complex conjugates. If the A's and B's are the same, but the sign in between is different, we call those complex conjugates. Okay. So this is how complex numbers come about, right? They show up in this way. You can kind of imagine this as being the output from the quadratic formula, right? If you had a negative discriminant of -9, this could be something you get out of your quadratic formula. All of these other things could just come from taking square roots in equations. So yeah, these are complex numbers. Any questions on how we calculate these things? Or how to deal with square roots in general? Square roots, I know, can be a little bit intimidating. Okay. All right, then let's take a look at a slightly more challenging problem. Suppose I give you a graph looking something like this. And we say that it looks roughly like this right here. So you can't exactly read off the vertex. Vertex is in here somewhere between, somewhere around -1, and the height of the vertex is somewhere between 1 and 2. But you can't tell exactly from the graph what it is. But I tell you the equation. This is y equals x squared plus x plus 2. Can you tell me how many zeros or roots does this thing have? How many real zeros or roots? Can we say anything about solutions to the equation x squared plus x plus 2 equals 0? Yeah, from the graph. So how many? How many zeros or roots does this quadratic have? Well, definitely it has no real roots. No real zeros or roots. Why? How do we know that? Are we getting that from something here? Are we getting that from something in the picture? What tells us that there are no real roots? Very good. Yeah. Because zeros are x-intercepts, or I should say real zeros. I'll use the word zeros and roots interchangeably. Are x-intercepts. And we can tell from the graph that there are none of those. Right? A zero is a number you could plug into this thing that makes the whole thing equal to 0. Well, that whole thing being 0 means y is 0, which means you're crossing the x-axis. So when we set these things equal to 0, we're finding x-intercepts. That's why we call them zeros or roots. So because this graph clearly has no x-intercepts, we know that this guy has no real roots. Okay, so what does it have? There's no real zeros or roots. So there must be 2 complex roots, or zeros, whatever you want to call them. Right, that's how this works. If you don't have any real roots, if you don't have any x-intercepts, then you must have complex ones. And those complex ones, they always come in pairs. You'll always get them 2 at a time. That's just because the way the quadratic formula works. You know, it's got that plus and minus built in. Or you can think of a quadratic equation, a degree 2 equation always has 2 solutions. Even if it's got 1 solution, it's a multiplicity 2. We'll talk about multiplicities a little bit down the road. So how do I find them? From the graph, we can tell that there are no real roots. That lets us know that there are 2 complex roots. How do I find those? I'm still looking for solutions to this thing equals 0, right? That's why we call them zeros. I'm looking for things that make this guy 0. If there wasn't a middle x term here, if it was just an x squared plus 2, then I could set this equal to 0 and solve taking square roots. But there is this thing, yeah. I don't expect to be able to factor because there aren't any real solutions. Remember from last time when we talked about the discriminant? We only expect to be able to factor if we're in that case where there are real solutions. And even then, only when the discriminant is a perfect square. So yeah, the only thing that leaves is the quadratic formula. X squared plus x plus 2 will be equal to 0 if and only if x is equal to negative b plus or minus the square root b squared minus 4ac all over 2a. I'll zoom in down here. So we plug in. B is 1, so negative b is negative 1 plus or minus the square root of b squared 1 squared minus 4 times 1 times 2, 4 times a times c, all over 2a, which is 2 times 1. So this is negative 1 plus and minus the square root of 1 squared is 1, 4 times 1 times 2 is 8. So this is 1 minus 8 all over 2, which is negative 1 plus or minus the square root of negative 7 all over 2, which is negative 1 plus or minus 7 is not a perfect square. In fact, 7 is prime. 7 doesn't have any perfect squares hiding in him. So the square root of 7 is just going to stay square root of 7. So this is negative 1 plus or minus I times the square root of 7 over 2. Or the two numbers are, i.e., the two complex roots, or complex zeros, are x equals, we can write this as negative 1/2 plus and minus I times the square root of 7 over 2. This is how I would write them like that. So this is negative 1/2 plus I times the square root of 7 over 2, and x equals negative 1/2 minus I times the square root of 7 over 2. The rule that I'm using when I split up these fractions is that a plus b over c is the same as a over c plus b over c, and it works fine with plus and minus. It's a nice little rule. So yeah, the quadratic formula is what we use. We just plug into our quadratic formula, simplify, and we first should simplify underneath the square root, and then we take care of everything else. So after we simplify everything under the square root, we have negative 1 plus or minus the square root of negative 7 all over 2. Now the square root of negative 7, just this piece, I rewrite as I times the square root of 7. That's the negative kind of popping out of the square root as an I. And then I split up the fraction. Splitting up the fraction looks like this. Just take the negative 1 over 2 plus or minus I root 7 over 2. That's following this rule. And then I write each one separately, right? The plus here and the minus here. So these are my two complex numbers. And if you were to plug either of these in for x in this expression and very carefully simplify, you will get 0. It's a little messy, but it would come out. a very reasonable question at this stage is, can you tell from the graph anything about these solutions besides the fact that they're complex numbers? Can I tell that there's a 2 downstairs? Can I tell that the part under the square root would be a 7? And unfortunately, the answer really is no. There's no easy way to infer the shape of the complex solutions from the graph. So we really do just have to rely on the formula, the quadratic formula here. Questions about this? Okay. So, answering this format only, 1 plus 3 over 2. I'm not sure what you're asking there, Mark, exactly. Is the answer in that format only? So, or could you leave it? Are you asking, like, could I have left this as -1 plus I times root 7 over 2? Could I have left this as -1 minus I root 7 over 2? You could. There's nothing wrong with these forms. But these are what are called standard form for a complex number, where you've got a plus I times b, a minus I times b. So we really do like to write them in this format. Is that what you're asking? Okay. Yeah, there's not technically anything wrong with leaving them like this. That's fine, they're still correct. But if the problem asks you to give the answer in standard form, right? Write your answers, complex numbers in standard form, then you do need to write them like this. And there are advantages to thinking of them like this. They're geometric in nature. The complex plane is a cool thing. I very much want to show you guys this stuff, but I don't want to overwhelm also. And since it's not an official part of the class, feel free to tune out for the next 10 seconds here. So I'll show you why we want the answers in that format. Have you ever graphed complex numbers? This is not something that you're required to do for this class. So the space of all complex numbers is called the complex plane. This is called the imaginary axis. This is called the real axis. And just like R is the space of all real numbers, C is the space of all complex numbers. If you want to graph the complex number A plus I times B, that's a 2-dimensional object, and it's right here. So when it comes to doing any sort of geometry stuff with complex numbers, like this is like the IY axis, this is like the X axis. The IB axis. For geometric reasons, it's nice to have them written as real part. A is called the real part. And B is called the imaginary part. So you go horizontally out the real part and then vertically up or down the imaginary part. And that locates this point in the complex plane. So if you're intending to do any further work with those complex solutions, we like to have them in standard form as A plus IB, separating the fraction out. But that's really the only reason from the perspective of this class that we would care about. And even, like I said, this stuff is something that we're not going to stress about in this class. You will learn more about complex numbers in pre-calculus if you choose to go on. Okay, that's enough of that diversion. So if you tuned out, please tune back in. I'm going to do 1 or 2 more problems of this nature, And then we'll be about ready to call it for the day. I don't want to move on to too much new stuff because this is where the test is going to end. So let me draw for you a graph. The function graphed below is ax squared plus bx plus c. All right, so it's a quadratic, standard form. Over here, over here, vertex here. Okay. And I don't really need to tell you anything else about this to answer the following questions. First, is the number A positive or is A negative? Second, is the discriminant b squared minus 4ac positive? Is b squared minus 4ac 0, or is b squared minus 4ac negative? C, is negative b over 2a positive? Is negative b over 2a 0, or is negative b over 2a negative? And then finally, is C positive, 0, or negative? I claim that all you need is this picture. You don't even need any numbers in the picture to help. Who can help me with the first piece? Is the number A the lead coefficient, right? The coefficient of x squared. Is the number A greater than 0, or is A less than 0? First, let's be clear. This means positive, right? If you're greater than 0, you're positive, and this means negative. A is less than 0. So is A positive or negative? Brooke and Kendra have some conjectures. Mark has a conjecture. There's a little bit of disagreement. So the way I remember positive or negative is that the inequality always eats the bigger guy. So here he's eating the A, which means A is bigger than 0. If you're bigger than 0, then you're positive. Here, the inequality is eating the 0, which means it's saying 0 is bigger than A, or A is less than 0. So this would mean A is negative. Okay, yeah, then it looks like we have a consensus. So A is positive. How do we know? This is correct. Because what? Because why? Yeah, because the graph opens up, right? If the parabola opens up like this, that means the lead coefficient A has to be positive. If the parabola opens down like this, that means the lead coefficient A is negative. It opens in the up direction. This is the open side that's facing up. So we know that A, the lead coefficient, has to be positive. All right, let's turn to part B here. The discriminant, this is a sneaky guy. Is the discriminant greater than 0, should mean positive, equal to 0, or less than 0, which would mean negative? here, this would mean positive, 0, and negative. Good, very good. Yeah, Mark's exactly correct. So I'll add these in here real quick. We really do want to get comfy with inequalities. This means positive, greater than 0. This means negative, less than 0. And it's true that the discriminant here has to be positive. And Mark gave the correct reason in the chat there. The discriminant has to be positive because there are 2 x-intercepts. Which means there are 2 real zeros, right? Every x-intercept is a real 0. So if you have 2 x-intercepts, then you have 2 real zeros, which means your discriminant has to be positive. If you have 1 x-intercept, that means you have 1 real 0. That means your discriminant has to be 0. And if you had no x-intercepts, that means you have no real zeros. That means your zeros are all complex numbers. That means the discriminant, which is the part under the square root in the complex and in the quadratic formula, has to be negative. Let me ask that same question. Well, we'll just do another version of this afterwards. So yeah, because we have 2 x-intercepts, we know that the discriminant has to be positive. What about negative b over 2a? When we look at part C there, is negative b over 2a positive, 0, or negative? What is this negative b over 2a thing? The thing up here we call the discriminant. The thing up here we call the lead coefficient. Yeah, negative b over 2a has something to do with the vertex. Which part of the vertex? Yeah, you're all correct. It's the vertex. It's h from the vertex specifically, which is also the axis of symmetry. So recall, negative b over 2a, that's h, which is the x-coordinate of the vertex, which is also, or AKA, the axis of symmetry. Specifically here, I would encourage you to think of it as the x-coordinate of the vertex. And it's that x-coordinate part that we have to be super duper careful remembering. So right here is h, right? And down here would be k, because this point, the vertex is h comma k. H is negative b over 2a. So it's this x value. According to the picture here, is h positive, negative, or 0? So this one would say h is positive. This one would say h is 0. This one would say h is negative. Good, yeah, Kendra's exactly correct. H here is negative. The x-coordinate of this vertex is to the left of the y-axis. All the x values over here are negative. Since h is somewhere over here, right, we know h has to be negative. Maybe this is -1, -2, -3. Doesn't matter. It's over here. Instead of being over here, it's over here, which means it's got to be negative. So in this case, I would say this guy, and I would say because the vertex is to the left of the y-axis. So H is negative. Right? All the points over here have negative x coordinates. Everybody comfy with that? All right, let's turn to this last one now. What about the number C? Is C positive? Is C equal to 0? Or is C negative? How could we tell? Well, if we plug x equals 0 into y equals ax squared plus bx plus c, then we get y equals a times 0 squared plus b times 0 plus c. So we just get y equals c. So when x is equal to 0, y is equal to c. What does that mean? When I plug x equals 0, I get out the number c. So the point 0 comma c is the what on this graph? Y-intercept, yeah, exactly. Perfect, bro. Yeah, it's the y-intercept. So let's come back up to my picture here. The y-intercept is this guy right here, and I know that this is 0 comma c. So based on the location of that y-intercept, can I say whether the number c is positive or negative?
It's positive.
Yeah, perfect, Charles. Thank you. Yeah, C has to be positive because all the points up here have a positive y coordinate, and C is the y coordinate of the y-intercept here. Therefore, 3 dots arranged like this means therefore C must be positive because the y-intercept is above the x-axis. All right, so which one of these says C is positive? The first one, the middle one, or the last one?
The first one?
Yeah, good. The first one here. This is the one that says C is positive. It says C is greater than 0. And we're getting at this from here. So the y-intercept on any graph of any function, is always 0, comma, whatever you get when you plug in 0 to the function. And since C is always what you'll get when you plug in 0 to any quadratic, C always tells you the y-intercept. All right. I wouldn't mind running through one more like this. I think it would be good practice if we have time. Where are we at with time here? 10:30. Yeah, we got 15 minutes. So these are fun problems, and I think they're worth doing. First, any questions on any parts of this? Sorry, don't mean to run away from it too quickly. Any questions on any parts of what we did here? Okay. Play the same game. With this guy. So here's the graph. Y equals ax squared plus bx plus c. First, is a greater than 0, is a less than 0, or is a equal to 0? Who can help me out with this? Is a 0, negative, or positive? Good, a here is negative, right? Because the parabola opens down. What about this next part? Is b squared minus 4ac positive, 0, or negative? I'm unsure whether Justine was answering part B or part A. So just to be clear, if you already answered, please just answer one more again. Is the discriminant here greater than 0, equal to 0, or less than 0? Yeah, very good, Mark. The discriminant here is less than 0. How can we tell? Good, because there are no x-intercepts. Which means that there are no real zeros. Is everybody comfortable why this thing being negative means there's no real zeros? It's the piece under the square root in the quadratic formula. And the quadratic formula is what tells you the zeros. So if the piece under the square root is negative, then the zeros have to involve the number I. That's the connection, right? So this piece from the quadratic formula, if he's negative, since he's under the square root, you'll get i's out, which means that there are no real solutions to that thing equals 0. And Kendra's got us on these next ones. Yeah, so the vertex, negative b over 2a, that could either be positive, negative b over 2a could be equal to 0, negative b over 2a could be negative. And in this case, negative b over 2a is positive, right? Because that's h right here. And it's to the right of the y-axis. That's a positive x value. Because h, which is negative b over 2a, is the x-coordinate of the vertex. And the vertex is to the right of the y-axis. Okay. And then finally, the number c. The number c here talks about the y-intercept, which is right here. This is the point 0, comma, C. And that y value is indeed negative because the y coordinate of the y-intercept is negative. Okay. Now, something I might ask you to do on a test, I might tell you a is negative, b squared minus 4ac is equal to 0, negative b over 2a is positive, and c is negative. And I might ask you to draw a graph that satisfies that. Or I might ask you to pick a graph that satisfies those from a list of graphs. So really quickly, I'll hold here just for a second if anybody wants to take a screen cap. Here's the graph. 5, 4, 3, 2, 1. Here's the questions and the answers. 5, 4, 3, 2, 1. Is the discriminant here positive or negative? Yeah, here it's equal to 0, right? Because we have one x-intercept. We have one real root. A here would be positive, right? Because your parabola is opening up. What about C? You can't really tell what the y-intercept is from this picture, can you? But can you tell me whether it would be positive or negative? Yeah, good. C here would be positive. Even though you can't tell exactly where it is, this thing is going up and to the left. So eventually when this thing hits the y-axis, it's going to be way up there. It's going to be very much positive. All right. You guys seem to be in pretty good shape with this stuff. So I will say, go ahead and finish up the homework. If you're having any trouble with any of the homework problems, come see me in office hours or send me a message on Canvas. The quiz 3 and homework 9 have been pushed to next Tuesday, which is the date of the test. The other thing that's going to be coming due next Tuesday is the review for exam 1 and project 1. Now next class, we're going to do an in-class activity, and then I'll hand out project 1. So make sure you don't miss next class. We're going to be doing one of those in-class activities. Those can't be made up. And I'll be handing out your project. So next Tuesday is the test. And the test is going to cover all the material that we've talked about so far this semester. And on that day, you will need to make sure you have handed in your project 1, your review for exam 1, which is on my math lab, quiz 3, and homework 9. Those are all going to be coming due on the day of the test. To review for the exam, I first recommend making sure you've solved all the homework problems. Then go back and make sure you've solved all the quiz problems and make sure you can solve them on your own without any help. Then I would go through the review in my math lab and also work on the project that I'll be handing out. We will be doing some review stuff on Thursday. Yeah, so Thursday before the in-class activity, I'll be taking homework questions from whatever you guys want. And then we'll do the activity and then I'll hand out the project. So Thursday is mostly going to be review, but along with that review, we'll be doing an in-class activity on this stuff. And then you'll have the homework, quizzes, and project to serve as review for you independently over the weekend before the test. Any questions before we skedaddle? Everybody knows how to join the office hours, right? I haven't been seeing a lot of you guys in office hours. That worries me. I get a lot of my calc students, but I haven't seen a whole lot of college algebra. So I just want to remind you to join the office hours. You just got to come here and click these links, right? So Monday, Wednesday, and Friday, anytime between 1 and 2, click this link. Tuesday, Thursday, anytime between 11 and 12, click this link, and that'll bump you right into the office hours waiting room. If I'm working with somebody else, you may have to sit in that waiting room for a second, just like in a real office hour. You might have to wait outside the office while I finish up with somebody, but I promise you I will get to you. So just be patient. Even if we have to go past 12 o'clock, I will get to everybody. All right, that's all I have for you guys today. Please wrap up everything through homework 9 and quiz 3 in Pearson as soon as you can. And if you get stuck on anything, please, please, please ask for help. The tutors are pretty good, but there's nothing quite like talking to the person who's going to write the test. And that's me. So don't hesitate to ask for help from me also. All right, take care, guys. I hope you have a lovely rest of your day, and I will see you on Thursday.